Good day, ladies and gentlemen. We are all welcome to the first lecture on Eeen202, which is electronics, measurements, and transducers. I would like to call attention of the students to take their time, watch this video over and over again, and if they have any issue that is not clear from this video, I encourage them to contact me for clarification. Without waste of time, I'm going to start by introducing the course. You can see the title says Electronics, Measurements, and Transducers. So what is electronics? This word electronics is derived from the name of electron. I know all of us can remember from our knowledge of chemistry that we have three elements in an atom. That is electron, proton, and the neutron. So the name of electronics engineering is derived from electron, and it has different definitions. The first one here is we define electronics as a science and technology that involves the motion, the movement of electrons and ions in vacuum. We said electrons and ions because the mobile charge carriers are not only electrons, but they are of two types. We have electrons which are negative, and we have what we call holes. They are ions which are positive. And also this movement is done either in a gas, like in vacuum tube devices, or in solid semiconductor devices that we designed using group 3 elements. We are going to see more on that. Another definition of electronics is the application that involves the control of the movement of electrons in vacuum, or in gas, or in a vapor, or in solid state semiconductor materials. And as I have said, these semiconductor materials, they are group 4 elements in the periodic table, as we are going to see. And this knowledge is used for fabricating different components, which include transistors, integrated circuits, that is ICs, and these transistors and integrated circuits are used for general application of electronic systems and electrical systems. Now, these electronics have another definition, which is said to be the study of information and energy processing. This is definition number 3. So what do we mean by the study of information processing? It simply means it is used in electronic devices like computers, like in bridges, like in routers, hubs, switches, multiplexers, splitters, repeaters, radio and television devices for communication purposes. So therefore, wherever we use electronics engineering for communication application, we define that as an electronics. And if you look at the second term in this definition, we said energy processing. What do we mean by energy processing? It simply means converting electrical energy into another form of energy, such as changing it from light to sound to mechanical energy to any other type of energy. So here we have seen 3 different definitions of electronics. So how do we understand the concepts on how electronic systems are derived? All we need to do is to remember that in electricity or in physics or chemistry, we have basically 2 types of charges. One of them is positive and the other one is negative. And we all already know that an atom has 3 basic particles, as I have already mentioned: neutron, proton, and electron. And we know that each of these elements, they exist independently in 3 different states. That is, any matter you see can be either in gaseous state, or in liquid state, or in solid state. And we have mentioned that in any atom we have 3 components: proton, neutron, and electron. So the first 2 particles, this is the neutron and the proton. They are located in the central part of an atom, which is called the nucleus. And the total mass of any element or any atom is concentrated in that nucleus. So what are we saying here? We are saying the proton and the neutron, which are located in the central part of an atom, they are the heavy of these 3 particles, and the electron is very light, because if we can remember, From our knowledge of chemistry, electron has a mass of 1/1850, roughly like this. So therefore, most of the mass of an electron is, an atom is concentrated in the center of the atom. The third element, which is not in the nucleus, we know it is what? It is electron, and it is located in orbits. They are the circular part around the nucleus. And we said this electron is negatively charged, and the magnitude of its charge is given by 1.6 times 10 raised to the power minus 19 coulombs. So the charge of proton is also the same, 1.6 times 10 raised to the power minus 19, but the only difference is that while the charge of electron is negative, that of proton is positive. While the third component or element in the atom, that is the neutron, is neutral in charge. It is not positive and it is not negative. Therefore, the net charge, that is the resultant charge, is concentrated in the nucleus and it is positive. And the other charge, which is negative, is concentrated in the circular orbit around the nucleus, and they are called orbits or shells. Now, knowing that in atom we have the circular part called nucleus, and around the nucleus we have orbits. Now we have what we call energy levels in an atom, and these energy levels, they are nothing but the different orbits around the nucleus, and the one that is closest to the nucleus, it has number 1, and the one next to it is 2, next to it is 3, up to that. And in each of these orbits we have electrons, and the amount of energy possessed by these electrons depends on the level in which they are located. You can see that any electron which is located in an orbit very close to the nucleus, it is subjected to a very high attractive force from the positive charge of proton. And because of this, we can say that electron is in the low energy level because of the much attraction it experiences. But if you go to the next one, the attraction reduces, so this is higher energy level than this. As you go further, you are increasing the energy level due to the reduction in the amount of what? Attraction. So if we understand this, we know that among these shells we have what we call the outermost shell, which is the one that is farthest away from the nucleus. And the electrons that are located in that outermost shell, they are called valence electrons. So for this, in any atom we have 3 energy levels or energy bands, and these energy bands are called valence bands, and we have conduction bands, and we have what we call forbidden band. And the outermost shell, as I have already said, it contains some electrons which are the strongest because of the smallest amount of attraction they experience from the nucleus. And those electrons that are existing in the outermost shell, they are said to be in valence bands. But whenever you have an electron that is detached from its atom and it is moving randomly, that electron is said to be in conduction bands. But we know there is no way an electron can detach itself from its atom and start moving without absorbing an extra energy that will enable it to do that. So the amount of energy required for the electron to detach itself from an atom is called forbidden band. So for this, we have 3 bands or energy bands. The first one is called the valence band, where our valence electrons are existing in the outermost shell. The second one, we call it conduction band. That is when the electrons have detached themselves from their atom and they are moving randomly, while the amount of energy required to enable them detach is what we call forbidden band. So this amount of forbidden band is of different magnitudes depending on the type of element we are discussing. So for us to understand this, let us look at these 3 diagrams. And here we are going to consider 3 types of elements with respect to these 3 bands existing in them. The first ones are called insulators, the second ones are called conductors, and the third ones, they are called semiconductors. And what is the reason why they are given all these names? The reason is simply because the amount of energy required to detach electron from the valence band into the conduction band is different from insulator to conductor to semiconductor. Now if you look at this diagram, that is figure 1.3, you see that here I have this shaded part. It is standing for my conduction band, and this one below it is called the valence band, and this is where my electrons, the outermost electrons, are existing. Now the amount of energy required for electron to jump from the valence band into the conduction band, we call it forbidden band. And if you look at this for insulators, it has a very high value or large value because it is in order of greater than or equal to 5 electron volts. And this electron volt, as you know, 1 electron volt is equal to 1.6 times 10⁻⁹ joule. What am I saying? The electron volt is very, very small in magnitude, but I am saying 5 electron volt is very large energy. I want you to understand, for something to be big or to be small or to be moderate, it is relative. It depends on what are you using to compare that thing to make it either large or small or medium. So this comparatively, it is called very large amount of energy, because we are going to see, if you come to semiconductors, yes, we have 3 distinct energy bands. We have our forbidden bands, we have our valence band, and we have our conduction band. But if you look at the band in between the conduction band and the valence band, you can see that its thickness is very narrow compared to that of what? Insulator. So that is why we say this of insulator is very, very large. Therefore, that of the semiconductor is now moderate or in between. But if you come to the conductors, you see that we don't have any band existing between the conduction band and what? The valence band. Meaning, the conduction band and the valence band, they superimpose with one another. What are we saying? In conductors already, our valence electrons, they are delocalized. They are not attached to their shell, but rather they are free to move randomly in the element. Typical example of these conductors are metallic devices. If we can remember our bonding method in chemistry, we know there is what we call metallic bonding. So in metals, the electrons are free to move, and therefore there is no need of any amount of energy to detach the valence electrons into the conduction band, and therefore we don't have any forbidden bands between them. So now if we go to the semiconductor devices, they are the ones that have moderate amount of what? Energy for electrons to move from conduction band into, from the valence band into the conduction band. And at room temperature, the thermal energy, because the room temperature is completely different from what? The absolute zero temperature. At the absolute zero temperature, no any heat energy applied, and therefore in the semiconductor, all the bonds are what? Intact to one another. But when the temperature rises to room temperature, some electrons will absorb enough energy that will make them detach themselves from their atoms, and they now start moving randomly in the element, and therefore they move from where? From valence band into the conduction band. And whenever the temperature is raised above the room temperature, more electrons will break from their valence band and they will go into the conduction band. So what are we saying here? We are saying as the temperature increases, the amount of energy supplied to electron is also increasing, and therefore it will have sufficient energy to detach itself from its atom into the what? Free conduction band. Hence, whenever the temperature increases, more charge carriers are produced, and therefore the electrical resistance or resistivity of pure semiconductors is what? Decreasing. Because whenever the conduction increases, definitely the resistance or resistivity is what? Decreasing. So therefore we are now saying these semiconductor devices, they are positive temperature coefficient elements. What do you mean by positive temperature coefficient? We are saying whenever the temperature increases, their resistance is what? Decreasing, hence their conduction is what? Increasing. So because of the conduction increase as a result of increase in temperature, we call them positive temperature coefficient. Now This semiconductor devices, basically they are made using group 4 elements, and the commonest among them that are considered for this purpose, they are given here. We have carbon, silicon, germanium, and we have tin. Now we can see two cups here that are meeting at this point, this one cup and this the other. So the gap between the upper cup and the lower cup is the one that is telling us the amount of energy required for conduction to start in that material. So if you look at this, the energy gap in carbon is bigger than that of silicon, and that of silicon is bigger than that of germanium, and that of germanium is bigger than that of what? Tin. So we can say the carbon has the highest, the tin has the intermediate, while the silicon and germanium, the tin has the lowest, and silicon and germanium, they have the intermediate. So what we are saying here is this carbon can be approximated to insulator because of its large energy band or energy gap, and the tin can be approximated as a conductor because of its very small energy gap. But the silicon and the germanium, they have intermediate, and therefore we can use them successfully as our semiconductor devices. Now, if you understand this, the next thing we need to do is the conductivity in crystalline solids. Let us assume that this is a solid material, and you can see this central part that have positive sign, they are our what? Nucleus. And we assume here we have electrons outside the nucleus, that is in the shells. So it depends on what type of element do we have. If this one is a metallic element, all these electrons, they are free to move around from one atom to another, and for this reason we call them conductors, because we don't need any extra energy for us to detach electrons from their atom for conduction to start. But if they are not conductors, if they are like insulators, all these valence electrons, they are tightly held to their atoms, and therefore they cannot move. And they are also tightly held in the semiconductors, but the amount of strength is smaller than that of what? Insulators. Therefore, applying a very moderate amount of energy can detach the free electrons, and they'll start moving from one atom to another. So that is what I have already explained. The metallic materials, they have free electrons to move, and these mobile electrons, they are the charge carriers that carry electricity and heat from one point to another of the material. All the metallic substances, we know they have free electrons because of what? They are metallic bonding, and they are categorized as conductors. But silver and copper and aluminum, they are exceptionally better than other metals. And non-metallic materials, as I've already explained, they don't have free mobile electrons moving from one atom to another. They are fixed, so therefore they are termed as what? Insulators. But in the insulators, the energy is very, very high. In the semiconductors, the energy is a moderate in between the two. Now, the materials that have this moderate amount of energy required in order to detach electron from its atom, they are called semiconductors. And as we have seen from our previous graph, we basically use silicon and germanium as what? Our semiconductor devices. And sometimes we introduce some metallic substance into these semiconductors in order to raise the level of what? Their conductivity. So in short, elements or components or atoms are categorized into three. We have conductors, we have insulators, and we have semiconductors, and I have already explained their properties. What differentiated them is the amount of what? Energy required for electron to be mobile. In conductors, no need of energy because the electrons are already delocalized. In insulators, we need very large amount of energy. In semiconductors, we need a moderate energy which is smaller than that of what? Insulators. So the next thing here is to look at the conductivity in these semiconductor devices. These semiconductor devices, as I have already said, they are group 4 elements, and in group 4 element, the kind of bonding they have, we call it covalent bonding. That is where neighboring atoms will share their what? Exterior or external electrons in the outermost shells. And let us look at this group 4 element. They have 4 valence electrons. Let me assume this is one atom, this is another atom, and this is another atom, and this is another. 4 of them surrounding this central one. Therefore this one will bring one atom out of it, 4, and this one will give one to share. Then it will share one with this, it will share one with this, and it will share one with this. So in this condition, all the external electrons of this atom, they are shared with 4 neighboring atoms. The same thing with this, the same thing with all of them. So in this case, when it is at absolute 0 temperature, there is no any heat energy supplied to it. Therefore all the bondings are what? Held strongly, and therefore we don't have free charge carriers. And therefore, when there is no energy, our semiconductors are now behaving as what? Insulator material. But when you apply source of energy, that energy can come from heat, it can come from what? Electricity. It can give the valence electrons more energy for them to break their covalent bands, and they are now free to move in a conduction band. And whenever this energy is given to them, they are now behaving as what? Conductors, because they have free charge carriers. And whenever an electron has broken from one of these bonds, it leaves a place where excess positive charge exists, because we know electron is negatively charged. So when it is detached from one place, that place needs an extra electron to neutralize it, meaning it is now a positive. And that place, we call it a hole, and it has a positive electric charge. Now, these semiconductors also, they are categorized into two. We have what we call elemental semiconductors, and we have what we call compound semiconductor devices. This elemental is from what? Elements. The semiconductors that are made of only one element, like silicon, like germanium, all of them, we call them elemental semiconductor devices. But the compound semiconductors, they are made of combination of other elements, like a compound in chemistry. And typical example here is aluminum, gallium, indium phosphide. How many? 4 of them combined to give us one semiconductor. And because of combination of 4 atoms, we call it compound semiconductor. I have already said that the elemental consists of germanium and what? Silicon. And the thermal stability of these semiconductors and the availability of advanced technology in these semiconductors is now being used in order to define or to design different types of semiconductors with different level of conductivity. And the semiconductors are categorized into 2 broad classes. One of them is called intrinsic semiconductors, and the other one is called extrinsic semiconductor. The word intrinsic simply means internal, it means pure. That is where we have pure semiconductor without introducing any impurity into it. And this is the one that we have already explained, using either silicon or using what? Germanium. But we have what we call extrinsic. We are going to see how they are produced. And as we have said, for this intrinsic semiconductor, whenever the temperature is at absolute 0, no breakage of bonds, no free charge carriers, and therefore the conductivity is 0. It is behaving as an insulator. When the energy is supplied either from heat source or from electricity source, the bonds are broken and the charge carriers are produced. Therefore, it is now behaving as what? It is behaving as a conductor. And the intrinsic semiconductors, they are the ones that involves introduction of external substances. That is why we call them impure. That is, we get other group of elements and introduce them into the pure group 4 elements. We are going to see what type of elements do we use and why do we use them. So, as we have already explained, in the pure semiconductor, whenever there is thermal agitation, that is excess heat energy, there is breakage of bonding. When the bondings are broken, we have free charge carriers, and the movement of these charge carriers creates a current, and that current we call it diffusion current. And also, whenever you apply electric field, because we said 2 types of energies, either heat energy or electricity energy. So whenever you apply a field, that is electric energy, to the pure semiconductors, they have more energy to break their bonds, and we have charge carriers, and these charge carriers will be moving with an average velocity, and we call that velocity a derived velocity. And we know whenever charge carriers are moving in a conductor, a current is what? Generated. we call that current a derived current. So therefore we have two types of what? Current. The first one is the diffusion current as a result of thermal energy. The second one is called the derived current as a result of electric energy. And we have already said the silicon and the germanium have intermediate energy bands. So these are their energies. That of silicon is around 1.12 electron volts, and that of germanium is around 0.72 electron volts. What we are saying here is that the amount of energy required for silicon to break its bonds is higher than that of what? Germanium. So the next thing is to go back to our flow of charge carriers. Whenever charge carriers are moving, we know they move from one region to another. As they are migrating from one point to another, we have variation in the concentration of charge along the length of the device or the material, and that is what we call charge concentration gradient. And whenever there is this charge concentration gradient in semiconductors, definitely we have free charge carriers flowing, and movement from region of lower concentration to the higher concentration, we call it diffusion. And the amount of current created as a result of this diffusion of charge carriers, we call it diffusion current. And one thing we should remember, we said whenever the bond is broken, we have two charge carriers. That is, we have electrons which are negative and we have holes which are positive. So now each of them, the electron and the hole, they have what we call mobility. The mobility is a constant that shows the relative significance or the relative strength of their what? Velocity in terms of movement from one point to another. And that mobility is represented by this symbol mu. So the amount of current that is generated either in the positive or in the negative. The positive stand for the holes because they have positive electric charge. The negative stand for electrons because they have negative electric charge. So the current, the diffusion current in the holes is proportional to its mobility, and the diffusion current of electron is proportional to its mobility. And you know, if you remove these proportionalities, you can put constant k. So now if I make this an equation, and I divide it, the first equation by 2, I'm going to get the current, the diffusion current in the holes all over the diffusion current of the electrons is equal to the ratio of what? The mobility of the holes to that of the current. And we have a voltage, we call it volt equivalence of the temperature, and it is equal to ID, that is the diffusion current all over what? Mobility. This mobility can be that of electron and it can be that of what? Hole. Now the value of this volt equivalent temperature is given by Vt equal to kT all over Q, where this K is a constant. We call it Boltzmann constant, which is equivalent to 1.38 times 10 raised to the power minus 23. And this T stands for our temperature in Kelvin, meaning if the temperature is given in degrees Celsius, we add 273 to it in order to change it to what? Kelvin. And this Q stands for the charge of an electron, which is another constant. It has a value of 1.6 times 10 raised to the power minus 19 coulombs. Now, we have seen that we can have pure semiconductors which are intrinsic, we didn't introduce any foreign substance to them, and we can have impure which are called extrinsic, we introduce an impurity to them. So now, the pure ones, as we have already seen, they are either silicon or germanium, and they are the ones that we use for fabricating our transistors, our diodes, and also for fabricating of carbon resistors. And they are called intrinsic semiconductors because they are pure in their form, no any foreign element is introduced into them. And I have already said, when the temperature is absolute zero, all the bonds are intact, no conduction, therefore it is what? Insulator in that case. When the temperature rises to room temperature and above, bonds are broken and the charge carriers are produced, therefore it is behaving as a conductor in that case. But what's the problem? The problem is that the average number of bonds that are broken for 1 mole is equal to 10 raised to the power 11 cm cube. And if you remember, our Avogadro's constant, it is 6.2 times 10 raised to power 23. So we now eliminate 6.3 just for approximation purpose. We have 10 raised to power 23. Now, if you say 10 raised to power 11 divided by 10 raised to power 23, it will give you 1 over 10 raised to power 12. And 10 raised to power 12, we know it is what? A trillion. That is only one bond is broken per 1 trillion bonds. 1 over 1 trillion is like 0. It doesn't have any significance. So what we are saying here, the pure semiconductors which are intrinsic, they have very low amount of conductivity, because on average only one bond out of 1 trillion is broken as the temperature rises. So this conductivity is not sufficient. And if we want to look at it in clearer picture, look at this diagram giving us the number of bonds broken with respect to the rise in temperature. You can see the temperature when it reached 450 Kelvin, the number of bonds broken is only 10 raised to power 14. If you say 10 raised to power 14 all over 10 raised to power 23, it will give you 10 raised to power 9. That is 1 over 1 billion. Even with this increase in temperature to 450 Kelvin, the number of bonds broken is very small. Therefore, the conductivity of pure semiconductors is not sufficient. Okay, so still on this intrinsic semiconductors, I have told you that whenever an electron breaks from a bond, it is leaving a hole in that place. Meaning, if one electron breaks, we have one bond. If two electrons, we have two bonds. Meaning, the number of electrons, they are equal to the number of holes. So we call this P to stand for the number of holes, and the N to stand for the number of what? Electrons. This N we know negative, and what? P stand for positive. So now this N times P, that is the number of electrons times the number of holes, is equal to Ni square, where this Ni we call it intrinsic concentration of the charge carriers. And we have seen a graph that is telling us the relationship between the number of bonds that are broken with respect to the rise in temperature. This is the typical equation we use for determining the intrinsic charge concentration as a function of temperature and other parameters. Here we have Ni square equal to A T cube exponential minus Eg all over KT, where this A is a constant of proportionality, T is the absolute temperature, which is supposed to be in Kelvin, Eg is my energy gap, and K is the Boltzmann's constant, which is 1.38 times 10 raised to minus 23 joule per Kelvin. Okay, so gentlemen and ladies, what I want you to understand from this first lecture is that even when the temperature rises in the pure semiconductors, the number of bonds that are broken is very small in each 1 mole, and therefore the amount of conductivity is also very insufficient. And this is the reason why in our next lecture we are going to see how this problem is solved by changing from intrinsic semiconductors to extrinsic semiconductors. Thank you very much. I advise you to watch and watch again. If you have any problem, contact me for clarification. Thank you.